Okay, so good evening, everyone. How was the exam? How was the exam? I mean, no response. It was not too difficult, right? Hopefully. Okay. What is it? Yeah, but it was difficult. No, it's okay. I think the lecture sample exam questions were more conceptual. I mean, more, I guess, long form, whereas the exam questions were more short. We'll see. I mean, we'll calibrate based on how people have done. I mean, the next exam. Okay.
When will our scores for the first two assignments be updated?
They're not updated yet. But it's anyway disconnected with the exams, right? So it's not.
No, but like other off the topic.
Yeah. So I have to ask Manas on that. So definitely before the spring break. What is it? Extension? No, before the spring break. So I asked her to prioritize the midterm exam actually. So we pretty much have these scores actually, but we're waiting for a few more, couple of more days, and then we'll release the scores. So, any other question about the exam? I mean, we'll not discuss the exam questions here. Hopefully, Menas can discuss them in the recitation next time, or I can discuss it next week after the exam procedure is over for everybody. Okay. So, yeah, let's see. So there are two things. First is I know you're busy with the assignment submission, but right below that is the project information. How many of you have actually opened it and seen the instructions? Because this is going to be actually, the project component is not going to expect, something more complicated than what you're doing in assignments. What you're working through in your assignments is depending on your background. If you haven't seen Python, it's going to be challenging. That we know, right? So try to think about the project. What would you like to do? Talk to me ideally, so that I can tell you, if it's too ambitious or if it's too easy, or try to, of course, think of something interesting. Project is a big component, right? So try to do a good job with the scoping out what you would like to do, okay, in the next couple of weeks. The second thing is about the assignment itself. So how many of you, I've seen some questions on the forum, and some of the questions I did not yet answer, but I'm hoping some of you guys can answer the questions. But anyway, today, right now, like, what is the biggest challenge with the two questions? Let's say, if I can give you some hints. Okay. So first question, RNN for language modeling. The first part of the first point is fine, right? It's just a Markov model. So you just have to do, don't worry about writing efficient code in the first try. It's important to get something correct, small scale, on your own laptops. Okay, so that's why PyTorch is useful. You don't have to push your model and optimization to device. Model and variables to device. You can actually do something really small, keep dimensions really small, and see if the whole thing executes. Okay, it's essentially like working with NumPy. So Markov model should be fine, right? Or is there an issue with even the first n-gram Markov model? What is the issue? It's fine. Speak out. What is it? Data preparation. But I think data preparation, you can get it from this particular script, right? So let me open that script actually. I actually have it running. So I agree. So understanding the nuances of torch text does take time, but you don't need to actually, like, you can run these first like 3 cells, and you can get this data, right? So don't worry about splitting training to test. Let's say you did this, first 2 cells, right? This is where the data is being fetched. So the IMDb data is getting fetched. Text and label are something called fields. We just define what are the constituents of each word essentially, like a vector associated with a word. What is the number for that word? What is the word for a number, and things like that. Okay. But once you get this training data, yes, this particular data set is about sentiment analysis. So there's labels as well, but we don't care about it. So if you look at, in this case, they've printed the first example. You can see that you can just fetch this. This is a dictionary, right? So you can just fetch the first list of words. Okay, these are tokenized, and this is your data. Okay, so you can just run a for loop and just ignore this training data if you want, and get only this text data, and you don't care about the label here. Okay, and then you can proceed, right? So once you have the sequences, you know how to build a Markov model. I mean, this is just a list. You can get huge lists like this for every review. Maybe even concatenate them, and for every few words, you want to predict the next word using a Markov model. That's fine.
So for predicting the next word, we have probabilities for all the different words, right?
Yeah.
And then so we need to sample from the probability to get the different output every time, right?
Yes. So there's a SciPy module, SciPy function, scipy.rb_discrete. You can use that if you want. There are different ways to do it. I mean, you can actually do it from scratch as well.
So but when you're sampling it, it can be a word with the lowest probability also. So we don't know that.
Yeah. So that's what. So I think a part of the question is asking just sample a few things and right this. Sample a few phrases starting from this first few words. Yeah, it could give. I mean, so given the size of the data and the quality of the n-gram statistics and so on, it may not give you a interesting sentence, but that's fine. It's fine. I think the same thing done at scale is what kind of works, and this is pretty much the state of the art in production systems. I mean, not this, but for example, the second question, this neural translation architecture, that's the bare bones, and then there are a lot of tweaks to that to get to an actual Google Translate, for example.
So the second question is the third part when you're saying. Second question, third part.
Yeah.
Second question, third part.
So let's do first question first, and then we'll get to the second question. Yeah. So first question is, so Markov model is fine. What about the second part? Is that also is somebody finding it difficult to build this model based out of sample sentiment analysis script?
Basically, I think the size is very I should not posted that random disconnector.
Yeah.
So when I try to run with a 10% training example, it is running, but still like when I try to increase to a 50%, it's not running.
So you are able to. So his question. So it's a good point, and you bring it up. So you can actually don't have to use the whole training data, just subset it, right? You can only use 10 of the reviews, 100 of the reviews, and actually run the whole script. So you know that the whole RNN architecture with embeddings or whatever, without embeddings, works, right? Then you increase the size. Of course, if you use a Jupyter notebook, you need a steady connection. But you can actually export this thing as a Python file and run it on the server in a screen session, and it'll execute. But of course, you need to log some pickle files in terms of like the error curves and so on, if that's asked. So that's a little bit of a difficulty if you're facing connection issues. It's not. So I logged in and I didn't see any heavy load. So sometimes if some user is using all the memory and all the memory or something like that, then you probably cannot log in or you get disconnected. And sometimes it happens, but this is not the case. Yeah.
Because like when we are trying to run, we are trying to run like 10% training example, and there's 1,000 words. Just 1,000 words.
Yeah, so vocab size will be 1,000. That's fine. I mean, you need to have the whole thing running, and you need to understand that it's working fine. So maybe for some teams, you are facing a different type of issue, which is scaling. Okay, but for some teams, maybe you want to understand basically. So before getting into the RNN, you need to understand what's going on in this script. Okay, this is usual classification problem, right?
Like the iterator. Like in the text document,
Yeah.
it is mentioned that is for sentiment analysis. So another iterator is there that creates a target which has an offset 1.
Yeah.
Which will be used for the loss function.
The iterator is to just get the batches, right? I mean,
just get the batches.
Yeah.
But the output should be offset 1 of the input, right?
Sure. So that is true. Yeah.
So like the bucket, we are not getting that output
Got it.
Which is giving positive and negative.
Yeah.
So the other iterator which automatically creates that expects one single corpus as the whole review. But
so you can concatenate all this list, right? So the highlighted thing, you can concatenate it as a huge list of.
Then it says some like sort key not found for iterator. That iterator doesn't run.
Okay, so if you don't want to use, so using the iterator depends on you reading the documentation well, and there could be some hiccups there. You don't have to. So you can actually use, so the first part which created this train data, right? Train data from, okay, where is the iterator?
You can actually use the input part of the bucket iterator to make your labels too.
Okay, so you're saying this bucket iterator or splits is not, you're facing, this doesn't give you the right batch, a right train batch and train right whatever validation batch and so on. So where is train iterator used? Okay, not here. Let's go here. So here, right? So what is this iterator? Oh no, not there. Here you're passing it. Okay, so you're saying you would like to use some other iterator which gives you an offset of the words. Yes. Yeah, getting the targets. Yeah.
Vector of vocab size. With offset 1 in terms of.
Sure. So if you can use that other iterator, but so that's fine. That's again a question which is like I don't know if it's fundamental. You can always write. You don't have to use iterators. Okay. You can, for a small scale data, you can actually literally for loop through, create your own batches. And even if you're losing, let's say this offset of +1, let's say your review is of certain length, okay, and I'll show you one example in a couple of minutes. Let's say your review is of 1,000 words, okay. Sure, you're not getting 1,000 plus 1, or let's say you created, let's say it's 1,000 plus 1 length. You need an offset so that the last one you need to have so for each example, you need to have the next word, right? So you can always use the review and index appropriately so that you're losing some data at the edges, but you can actually just use the training data, the list of words that you're passing to the RNN. You can just create the comparison, the true labels, or in this case, true words, directly from the list. You don't need to have like a 2 copy. I understand you can use an iterator, but you can directly work with just the input, which is a sequence of words. Okay, people who didn't understand that, it's fine. But first point. Okay, coming back to the first point, you need to understand this script really well. Okay, and you'll see that it's using extending an N module. It's doing few things like having a linear layer here, having an embedding here, and it's actually learning that embedding. Okay, and the question was about. Actually, somebody asked me a question: should we change this embedding to a globe embedding? You don't have to do that. I think in the assignment we have not asked to change globe embedding here. Change the embedding here, but you could use a pre-trained embedding layer here.
For the second model, we have to use the embedding weight, like we have to copy those weights.
Yeah, for the second question. So the first question. I'm just discussing the first question. Yeah. So anyway, this is a standard layout template, right? You initialize your module and have a forward operation. And here, for example, you can see that you're only picking the last output. So actually, you should look at the documentation for nn.rnn, okay, and the PyTorch documentation. RNN, it accepts a sequence of inputs, and it creates a sequence of outputs and gives you the last hidden vector, okay. In the sentiment classification, you don't care about intermediate outputs. You care about the last one. That's why there is some reduction in dimension. And this is an assertion anyway. So they're looking at only the last hidden output, and that's the same as the output. That's the previous assertion. But anyway, so they're only using the last output, last entry, right? So in your case, you'll have intermediate outputs, and you can try to use those intermediate outputs to see whether the intermediate output is close to the expected word you have, the word you care about as the next word. Okay. Do you understand what I'm saying? So in language model, you probably have to use the whole output sequence rather than the last one. Okay. So that's a semantic difference, and you can decrease these numbers as needed in case you're running out of memory or. Okay. So this is standard definition of a loss function and so on. So here, actually, I added a thing. So important thing to use. So there are two tools that you can use to get rid of your bugs that you're facing. One is documentation. So torch text and PyTorch documentation in this case, NN modules and variations, right? NN.RNN, NN.LSTM in this case. Second thing is either you use either you use print statements, have the for loop, have the iterator only run, and instead of functions, maybe remove this function and have a for loop which is like 1 step or 2 steps and literally print out and see what's happening. Or you can use SetRace. That's a cool part. You can actually debug. Okay. So for example, here I've put SetRace here to understand what RNN is doing. So the RNN module or the model here is actually doing. It's not letting you do the for loop for every RNN step. It's actually taking the sequence and already outputting you a sequence. Okay. So that is something you're already getting for free. Okay. So you don't have to do any for loop on every few words and try to predict the next word. You don't have to do that. Okay.
How do you get the output? You said right, intermediate output and set that.
Yeah, so these outputs, so here I'm just outputting the last one, right? So I mean, in the script, we are just outputting the last one. You can just output the full sequence. Yeah, if you output the full sequence and then your criteria, I mean, here you're just using binary cross entropy directly. You'll have to define a function such that it can take, arbitrary length outputs and compare that with the embeddings, for example, of the true sequence. Okay. Of the true sequence of words. So you just have to probably redefine this criteria. That's all. Okay. So do you want me to execute and show you how SetRace works? I think I had it during the office hours, but do you want me to execute this and show? It's fine, right? So, huh? Okay. I mean, I'm not saying anything new here. So let's see. Actually, this was running. So let's see if this one works. Yeah. Yeah. Okay. So definition of the module, dimensions which you should reduce, and I mean, here we are just showing sentiment analysis anyway. So evaluate. Okay. Oh, what did I do? Oh, did I execute? Oh, I didn't execute this. Oh, runtime. So I have some other issue. Somebody's running. I think. I mean, we can check that actually. Who's running what? But okay. Yeah. Let's see. Let's take. I mean, after the break, maybe I can show this to you. Okay. So all I did was add a trace so that you can understand. So what I wanted to demonstrate was that inside the train function, I added a set trace. What it will show you is what are the predictions. Okay. So, or not just predictions, you can actually evaluate what was being passed to the RNN model. Okay. So you'll see that what is a batch. In this case, the batch size is 64. And the first example, since the set trace is set, you'll see the first batch. It is something like 1081 length, and you'll see some paddings in the batch because all reviews are not of the same length. So you can get an idea of what's being passed as input to your model, okay, and what's being output.
The main obstacle is the last function where we comment the output and pass that string of 3 words.
Yeah. So in this case, you have to change the last function because you are trying to ensure that every word being predicted in the review length, let's say 100 words. After for any subsequence, you are predicting the next word, right? So that's essentially you're trying to ensure that that output is the same as the next word's, for example, embedding vector, okay, or 0, 1, or whatever binary. What is it called? One hot encoded vector, for example. You could do that. Yeah. So you just have to change the last function. Okay. So let's. Okay, I think I told you too much about the first question. So let's go to the second. Any questions about the first part? First question? It's fine. So okay, next. So what are the issues with the sequence-to-sequence model? Is everybody able to at least do I think they do English to French, right? So are you able to execute it and see that it translates, right? The whole script, right? And were you able to change it to your language? That's something different. So any issues? So you had an issue, right? So
no, I wanted to ask that in the third part, let's say when I'm inputting a sentence like I like music and song.
Yeah.
So the output English translation that I'm getting is I like music and then few garbage words.
Sure.
It's not exactly the same. I'm getting.
Sure.
Or either some words are getting repeated
Yeah.
several number of times.
Yeah.
So that's fine, right?
Yeah, that's fine. That's fine.
To give exact English translation.
No. So the objective of this is a bare bones skeletal, neural translation architecture, right? So given the scale of the data,
some semantic similarity between the input and the output, then it's fine.
Even if it's even if the similarity is very less, it's okay, because this we know this architecture works. It's not like you're testing it for the first time and trying to figure out whether this is the right solution to translation or not. Pretty much this and variations of this are the state of the art today for translation. So it's just an exercise for you to go through. Actually, the most important point is step 2, where you want to see if glow increases, how glow impacts your accuracy numbers. Maybe you want to run a script without the embeddings, English embeddings, and have the embeddings and see the accuracy numbers or the loss numbers if they change a little bit. Okay, so that's like you introduce pre-trained vectors and therefore maybe performance increased or did not change. Okay. That at least you should be able to observe. The text itself, as you get more data, it may work better. Or there are a few other things like attention and so on. Okay. Yeah, so there are many different things which people have innovated on, which increase the performance. But for this, you don't need to do that. Yeah. So assignment is fine, right? Right. Yeah.
After using glove embeddings, the accuracy change, should it be positive or negative?
You should test that hypothesis, right? So you have.
It's bad, right? It's bad.
The loss
Quite poor. So with or without glow. So first of all, overall, I'm talking about relative numbers. Overall, anyway, maybe it's fine. It's worse. It's not.
The loss increases.
Okay, so try to think about why maybe it increases or not, right? So you're saying you have lesser parameters. You're using pre-trained embeddings. Oh, maybe you are updating those embedding values as well. Yeah, I mean, think about this. That's a part of your assignment. Yeah. There was another question in the back. Oh, so you should. So where you have this, where is the initialization of the RNN module? Yeah, so you should use the pre-trained embedding here. So how do you get that? So torch, the text.vocab. Just look at its document. So yeah, look at torch text documentation. It will tell you how to use these embeddings. Pre-trained vectors directly. So it's just essentially a function call, and you should use it and replace it here.
What's the function over there?
Here it's just nn.embedding. Okay.
No, but the one on top, like the main function.
Oh, this is an RNN definition. Yeah.
We'll copy the embeddings after we create an instance of the second encoder, right? And then after we create
Second encoder, there's only one.
The model, the second model, when we create the encoder,
Yeah.
we call the encoder.
Oh yeah, that's different. Yeah.
That, right?
Yeah.
We won't initialize
No, not here. So this is not the second questions code. Yeah, this is just a one RNN, right? So you need an encoder and a decoder on the other one. Yeah, it's different. Yeah, you need to place it appropriately, but you will have a similar module. Yeah. Okay, so actually that's good. So I think people who are seeing Python for the first time, you'll face some challenges, but that's fine. It's a learning experience. So don't try to get to state of the art, or you're not getting state of the art. That's not the goal. The goal is to understand the choices and trade-offs. Okay. With that, let's start today's lecture. Actually, so today we're going to talk about a different topic. So I was thinking of doing this later towards the end of this course, but I thought let me do it now because the kind of complexity that you've seen with CNNs and then RNNs, and then later on with various lot encoders or GANs, that's pretty much like beyond that each one requires a lot more detail. So things like choice of optimizer that you probably are using, like Atom optimizer or SGD versus something else like RMS prop or whatever. There's several names. I think knowing that those differences is not as crucial as understanding yet another toolkit in your box. So that's why I decided to pick this topic. So there was also another lecture which was prospectively titled PyTorch implementation. So that I think we'll do it offline, in the sense as maybe I'll create a video or something and share it with you if needed. Okay. So that anyway we'll have to anyway revisit that topic, because many of your projects will involve probably PyTorch as you think about your project for this course, right? So then we'll do something on a need to know basis. Okay. So for the next 4 lectures, okay, will be about graphs, but 2 different views of graphs. Actually, the next lecture will be about graph convolutional networks, so graphs and deep learning. Today's lecture will introduce graphs, of course. So just to kind of warm ourselves up with what are the components of a graph, and then the second part of today's lecture will talk about graphical models. So we've already seen. I think we discussed LDA when we talked about text analytics, right? When we talked about text data, right? We talked about latent digital allocation. So it's a graphical model. So and not just that, naive Bayes classifier, you can think of it as a graphical model. Even linear regression, there's a graphical, there's a Bayesian version of it, which you can think of it as a graphical model. So we look at graphical models today, the construction and the concepts. After graph convolutional networks next lecture, we'll again look at how do we manipulate these graphical models and how do we learn these graphical models. So that's the sequence in the next 3 to 4. In between, there's graphs and deep learning involved. Okay. And then the last part of the course, last 3 odd lectures would be about online learning, which is kind of something related to A/B testing, but kind of useful in internet companies, advertising, healthcare, and so on, and of course reinforcement learning, which is an extension of, which is also belongs to that topic, that topic class. Okay, so today the sequence is as follows. We're going to try to understand what are graphical models. Okay, second, which is going to be crucial, is to relate. Can you guys see? Okay, is to relate a distribution to a graph, and reading the implied conditional probability assumptions. Okay, reading the implied conditional independence assumptions. Sorry. So that requires us to revisit, what's the joint distribution on a bunch of random variables. How is a random variable conditionally independent to the other? And the graph is such that it will help us understand what assumptions we are making. So we are in a world of, this toolkit is going to help you really embed your domain knowledge in a very parsimonious manner. So that's the strength of this toolkit. Okay, this bunch of tools. The third point is going to be, there are going to be 2 types of graphs. You'll see that there's going to be directed graphs and there's going to be undirected graphs. The difference is that certain assumptions can be encoded only in one graph or the other. So, but that's fine. We'll just understand kind of what can we do with these graphs. Okay, for both the undirected and directed versions. Any questions about the lay of the land for today? Some of you are looking Any questions about the context? I mean, we'll go into the further motivation next. Okay, so let's see. Okay, so why are graphical models interesting? At least for the CS community, there was a Turing Award recently given to Julia Pearl, which was about which was about, of course, developing a calculus for probabilistic and causal reasoning. But a big component of this causal reasoning or causal inference field is graphs. Okay, so kind of important. And so let's start with why graphical models. Okay, so there's a whole area. I mean, so as I was just in the previous slide, I said causal inference. So a big chunk of causal inference these days, where you want to attribute, something really caused something else, like your action, your marketing strategy really increase the sales, or your implementation of a certain policy, certain analytics really increase some numbers or reduce some costs. You have to really say that it's a causal link between them. You can't just say my actions are correlated with what happened in terms of sales, right? That's not enough. To say so, there's this whole field of causal inference which looks at how do you answer such questions. Okay, actually A/B testing is also related to that that type of a problem, and that also involves graphs. Okay, so the same preliminary ideas that we'll see in this lecture also underpin causal inference. So if you understand kind of the nitty-gritties, for example, for the directed graphs that I'm going to talk about towards the second part, it's kind of important. It'll help you understand how to use causal inference and make causal statements. Okay, but now we'll really not think about causality. We'll think about why graphical models. The second big point is that it helps us work with structured data. Okay, so that's fine. It helps us work with structured data, but more importantly, it helps us encode really rich domain knowledge. Okay, so think of just tabular data. Here the examples are not really about tabular data, but think of tabular data. Then you can really encode rich knowledge that maybe first something happens, somebody gets educated, and then they get certain type of job. Okay, so that's domain knowledge. If you just look at a table as a bunch of numbers, you don't have that information, right? So you can encode domain knowledge, and we'll see how to do that. Okay. So because we are transitioning from deep learning to the notion of graphical models, so deep learning was all about determinism. Okay, everything was deterministic, right? The network is essentially a nonlinear function going from some input space to some output space. Whereas graphical models are inherently probabilistic in the sense that we are all going to think of everything as a random variable. Of course, there's only some parameters, but which drive the distributions which are related to these random variables. Okay, so what graphical models capture is dependencies between these random variables. Okay, so in contrast with neural networks, which is just input-output mapping. The third point is low capacity versus high capacity. It just means that with neural networks, you just saw in your assignment, you can actually build a translation object, right? You can go from English language to let's say French. Whereas, so that's a really high capacity task. It's a really complex task. You really need millions of parameters potentially to get really good accuracy. In contrast, low capacity just means here we are not really thinking of exploring the number of parameters. The parameters are just parameters related to these random variables. There may not be too many number. If you have 10 random variables, maybe there are 20 parameters. Okay, if each one is a Gaussian, there will be 20 parameters, mean and the variance. Let's say, if they're independent. So that's what I mean by capacity. The capacity is really, we're not thinking of fitting really large input and output spaces, some really nonlinear functions. Okay, and this is what I was talking about in the previous slide. That domain knowledge is what we can encode in this framework of looking at supervised learning or unsupervised learning in a very parsimonious way. Okay. So there's going to be 3 parts to the story. First is representation, which is this lecture. We'll kind of talk about what random variables are. I mean, we've already seen in supervised learning, input could be a random variable and output could be a random variable. And in 575 we talk about expected error, generalization error, and so on, right? So and a distribution between input and output. So there's going to be random variables. There's going to be uncertainty, and in terms of representation, we're also going to look at a key property between these random variables, which is conditional independence. Okay, that's what graphs capture. Yeah.
So in the graphical models, it's mentioned that there exists dependency between random variables, but doesn't deep learning capture this dependency?
Yeah. So the deep learning captures. Let's say input is a bunch of 10-dimensional vector. Think of tabular data for simplicity. And there's some output, you're predicting positive or negative, let's say some binary class. Yeah, so a deep learning architecture will capture a relationship between the input and the output, and it may have even if the coordinates are dependent or collinear in some way, or there's some correlation between them. Yeah, it's fine. I mean, it'll be taken into account while you're building the model. So
graphical models is important when you have small amounts of data compared to deep learning. If you have a large data set,
No. So graphical models is a unifying way to think about any of the supervised learning models that you've seen. Like I said, naive-based classifier. It's a graphical model. What is it? Something called a conditional random field, which is used for text processing, which is still used for like a part of speech tagging and so on. It relies on graphical model ideas. Okay, it's a way to look at all these different models. And we talked about latent digital allocation, topic modeling. It's a graphical model. Okay, so you can do both supervised and unsupervised learning tasks using a graphical model perspective, where you're thinking of objects as key objects being random variables and the relations between them. Whereas I guess when you think of deep learning, you are you're doing all these tasks as well, so both supervised and unsupervised learning, but you're thinking of the complexity, the unstructuredness of the data, the text data or image data. How do I deal with them? Right, so it's a slightly different focus. Both tools can be used for the same task. Yeah. A third point is visualization. When I say metadata, this is what I mean by additional knowledge. Okay. We'll see that in the in subsequent lectures. We'll look at inference, where the graph is also going to help us compute things which are conditional distributions. Okay. So remember, if you remember. Probability of a class given x, right? So this is a conditional distribution. So if output is a random variable, output is a random variable g, okay, input is a random vector x, then by training, essentially you're finding some parameters such that you can make the prediction that the probability, given the parameters, the probability that the output class is 1, 2, or 3 given x, right? That's a conditional probability estimation, right? So you'll see that we can get the same objects, we can get many other objects, okay, and that's the notion of inference. And learning is about estimating the parameters of the model itself. Okay, so that's the last part. So let's understand the model constructs today. Next, talk about if we had the model itself, then how do we estimate things like make predictions or estimate other things, in the subsequent lecture. And the last lecture would be about learning the parameters themselves. And the learning the parameters themselves, just to give you a teaser, it's related to maximum likelihood estimation and things like EM, expectation maximization, and so on. Okay, and to give you a teaser about inference is about things like Markov chain Monte Carlo sampling, okay, sampling from distributions and so on. Okay, there are a few things there. So let's actually directly get to a few applications, 4 applications. First application is what is called a hidden Markov model. So hidden Markov model has been used in various applications. Here I've said, speech recognition or part of speech tagging. So hidden Markov models plus Gaussian mixture models was kind of the predominant strategy for speech recognition before deep learning architectures. Okay, so things like I don't know if you've heard of Dragon naturally speaking or Nuance software. So so automatic speech recognition technology was based on hidden Markov models. Okay, so it's a graphical model. And so if you don't know this, so this is going to be the example graph, but we'll not go into the details of that one immediately. but essentially it's captured by like some sort of a joint distribution between random variables, in this case y's and x's. Okay, and the Markov part is just that y's only depend on the immediate previous random variable yt minus 1. So there's going to be a sequence of random variables in this model, and the random variable, current random variable at indexed by time t, only depends on the immediate previous random variable t minus 1, in the sense that given the t minus 1th random variable some value, the tth random variable has nothing to do with the t minus 2th random variable, so they are independent, conditionally independent. Okay, so anyway, so there's some distribution. I mean, this model is captured by a particular distribution form and a graph. Okay, and it has some under these assumptions there is some inference that you can do, compute the most likely sequence, or there's going to be some random variables which are hidden, which are these y's, and there are some random variables which are observed, so you can do estimations, inferences, like what is the most likely values that the hidden random variables took given that I've seen some observed random variables. Okay? Questions of that nature. At this point, I'm just motivating at a very high level, so you may not know the details of this immediately. Maybe we'll get to this when we talk about inference next, subsequent lecture. Okay, that's fine. The second, which we have seen this one already when we talked about natural language processing. So this is a graphical model. Actually, this is a random variable, right? This is the output class, spam or not spam, and there's a bunch of random variables, one indicator variable for each word in my vocabulary, okay, whether it's on or off, and so these are also random variables. And there's a particular graph that I drew here, with one output class and there are outgoing edges, outgoing arrows to all these n random variables, right? And there's a corresponding conditional probability distribution. So I will not repeat what Naive does because we've already seen this before. But this graph was not just a cartoon picture. There's this is the graph corresponding to a distribution. Okay, and there's also something called a plate notation, where instead of writing these n random variables separately, I just put a box and write I is equal to 1 to n for a single circle there. Okay, and the third application is latent additional allocation, which again we saw in a little bit of detail in the analytics in the natural language processing lecture. Do you want me to recall what the LDA model was? No? Yeah. So anyway, let's on the fly. I know it's an easy model to understand. There's a bunch of random variables. I just want to highlight that there are a bunch of random variables there, which is that first there's going to be a topic distribution. So think of a single document. So this is I think in that lecture I was talking about a generative perspective, right? So first we generate a topic distribution. That's a random quantity. Okay, that's a random vector. It just happens to be a distribution, but sums to 1. It's a vector. Okay, let's say you have 10 topics and it's a vector over 10 dimensions, sums to 1, so it's a distribution. So that's the topic distribution for the document I'm going to create. Now given the topic distribution, now I'll say let's say I want to create a document with n words. Okay, what I'll do first is create. Okay, I want to first figure out for each word which topic it belongs to. So for which I'm going to draw from this topic distribution. Okay, I draw a sample from this topic distribution. Let's say I have 10 topics, right? So my first word could be the first topic. My second word could be the third topic. It's the sample number could be 1, 3, again 1, maybe 4, or something like that. So for each word, I'll assign which topic it belongs to. Okay, so that's a random variable there, right? Assigning. So ZID is in this document D, the ith word, which topic it belongs to. Okay, and then once I assign the topics, I don't know the words themselves. Now I'm going to generate the actual document, the sequence of words. So for the ith location, if I said it's a topic, it's a topic is sports, then I'll go look up in a sports specific probability density function, probability mass function, and pick a word from that sports specific PMF. Okay, and that's the word I'll put in that location, ith location. Okay, so now again there's some randomness. I drew a sample, right? So that's how you create a document. That's a generative. We assume that this is how documents are created. There is no order relationship here, right? And under this assumption, now given the documents, you can infer what were the parameters of these distributions which led to this document. Okay, so that's the high level idea. Is that clear? Okay, I mean at this point it's just okay. There's an application which is related to graphical models. Okay. Last one is actually something called a conditional random field. It's actually used. It's used for example, actually many tasks in text processing. So, here I've not drawn what the graph corresponding to conditional random field is, but the conditional part refers to that there is a conditioning on features. Okay, so think of I have a sequence, a review for example, and I want to tag the words as nouns, verbs, pronouns, and adverbs, and so on. Okay. Then y is corresponding to the tag. So it's a sequence to sequence model, right? I given the input sequence of the sentence, I want to get the parts of speech. Okay, and you can't like look at each word and just say what part of speech it is. It depends on what are the succeeding and preceding words and what the sentence is, right? So what this particular model lets you do is find the probability for a particular tag sequence. Okay, given the tag sequence, it can tell you given the sentence, given the tag sequence, it can ascribe a number of how likely is that's the part of speech tagging sequence. Okay, and there are some assumptions about how to get the tag, but let's not worry about it. There's a distribution corresponding to this operation. Okay, and there's a graph also corresponding to it. So those are two objects: a distribution and a graph. And in the previous 4 examples, and this example, we saw there's a distribution and a graph. Okay. C is a bunch of it's like a collection is a collection of indices. So subsets of random variables. Okay, it's C is just indexing. Okay, maybe the first, third, and fifth random variable are the ones which will tell me the part of speech tag for the first word or something like that. Anyway, we'll go into the basics of graphs pretty soon. So yeah. Any questions though about the motivation? Are you convinced that it's an interesting enough thing to study, or at least something? How many of you have seen graphical models before? One person has heard of it. So who else has not? Huh? Actually, in 575, you must have seen Gibbs sampling, right? No? No? You are saying no or yes? No. Okay. So we'll see Gibbs sampling actually in the subsequent lecture. But you might not have seen graphical models in this generality, but you have seen some of the models, right? Naive-based definitely you've seen. Topic modeling, you might have at least called an LDA function in some package maybe, depending on if you did a project on text or not. So we've done various things. Hidden Markov model depends on whether you are from an engineering background. In engineering, people look at Kalman filters. Okay, so Kalman filters are essentially hidden Markov models on on continuous basis maybe. Okay. Okay, so next part is going to be pretty basic. So tell me if I need to speed up. Okay, it's about graphs. How many of you have seen some treatment of graphs before? Like what's a graph? What's a node? What's an edge? 50%. Few of you have not seen these terminologies before. Who has not seen treatment of graphs? Some of you. Okay, so. For the others, correct me if I'm wrong or if I'm too slow. Just tell me to speed up. Okay. So what's a graph? It's a should have not used a network, but it's an object with a bunch of edges and vertices. Okay. And it's heavily used in computer science. So people have seen some algorithms and algorithm pseudocodes or something like that. You must have seen graphs maybe. Here for us, it's just going to be a visual tool. It's going to encode some sort of a, as we said, there's going to be a graph, a distribution, so it's going to encode some sort of conditional independence properties on that distribution. Okay, so for us, it's visualization purpose today. So anyway, so here's an undirected graph. I just have no information. That's what undirected means. There is no directedness on this edge. For example, these are the there's 5 nodes and 5 edges, and there's no direction. Okay. Okay. So what's the notation? So set of vertices, people write as a V, but let me index the vertex as 1 to n, capital N. Then the size of the graph is n, which is number of vertices, and the edge is the unordered pair. Okay, so it's just the first index is a vertex number, and second index is a vertex number. Okay, that means that there's an edge. Here vertex number 1, 3 means there's an edge between 1 and 3. Okay, and the maximum number of edges is n choose 2 for every pair of nodes, if there is an edge or not. Okay, and if there is an edge, then n choose 2 is the number of edges. Okay, and nodes I and j are connected if there's a path of edges between them. Okay, so in the previous example, node 1 and 5 are connected because there's edges. There's a path from 1 to 5. Okay, and what's a subgraph? Subgraph is just restricting my attention to certain vertices and edges between them. Okay, so basically deleting other nodes and other edges going, which are dangling. So, and as I illustrated before, what's a path? A path is a sequence of vertices, or you could think of sequence of edges. It's the same idea. Sequence of vertices where each successive pair are connected by an edge. Okay, so if I say a path is 3, 4, 5, then 3, that's not correct, but anyway, 3, 4, 5 is not a path, but you can see that 3, 1, 4, 5 is a path. Okay, 3 to 1, 4 and 5, right? Okay, so we will care about paths towards the when we talk about conditional independence. So we care about paths, and so what's a neighbor? So we'll see. The concept of neighbor is also important. So a neighbor is all those vertices which share an edge with a given node. So given a node, I can tell you. Can you tell me who the neighbors are? That's the question, and it's basically all the vertices which are connected to me via an edge. Okay, so let's call it NBHD, short for neighborhood. Okay. Neighborhood of X. Then, for example, the neighbors of 1 are 3, 4, and 5, right? 3, 4, and 2, right? Okay. So next, so that's just a notion of neighbors and path and so on. So now let's look at slightly, I guess, a new definition: clique. Okay, clique and independent set. So how many of you have heard of clique? The ones who knew about graphs. Okay. Okay. So so what's a clique?
Complete graph, as in all the nodes in that clique will be connected to each other.
Yeah. So a clique is nothing but a bunch of vertices where each vertex shares an edge with the remaining vertices in that set. Okay. So they're all a bunch of vertices. They are all directly connected to each other. Okay. And an edge is also clique, by the way. An edge is also clique because there are two nodes. They're connected. One is connected to the other is connected to this. Okay, an edge is the smallest clique, let's say. What's an independent set? An independent set is a set of vertices whose induced subgraph is empty. In a sense, you pick far away vertices; they may not be connected to each other. Okay, so if you ask for the induced subgraph, there is no edge between them. Okay, that's an independent set. And there are some. So, for example, here, the ones in the square boxes in this green boxes are, for example, an independent set. Okay, and the one in this blue box is a clique because there's an edge between all of them. Okay, so each node has a degree of 3 or 3 edges essentially. Okay, so that was about graphs without any notion of edges, directions, directed edges. So now let's look at directed graph. Okay, and in particular directed acyclic graph. So what is a directed graph? A directed graph is basically edges with directions or orientations. Okay, so maybe there's a direction like this, maybe there's a direction like this, maybe like this. Then you kind of take that information into account as well. Okay, and so an edge UV means that there's a starting point is U and ending point is V. Okay, so there's a direction from U to V, and you may also have a direction from V to U as well, for example. Okay, that would be a different edge. And okay, what is acyclic? Acyclic is basically you should not have a directed cycle. Okay, and which just means that there should not be any way to follow the oriented edges, these directed arrows, and come back to the starting node. So pick any node. Pick any node, and you should not have a cycle where you follow directed edges and come back to this particular node. Okay, if you don't have such a phenomena in your graph, then it's acyclic graph, okay. Directed acyclic graph. So here's a directed acyclic graph. So you can verify visually that there is no edge, there is no cycle, okay, because of the direction of the edges. Okay, there's a direction in this way. If this edge was opposite directed, then there is a cycle. Okay, you can see that this one, and this one. So if it was opposite, then there would be a cycle. That's not a directed acyclic graph. Okay. Okay. So directed acyclic graph. I mean paths, DAG paths versus directed paths. So you can think of a path in a directed acyclic graph as well. When I say a path in a DAG, there's a nuance, which is that when I say a path, I don't mean the directed path. Okay. If I'm talking about a directed path, I explicitly will say a directed path. Okay. So in for example, here there's a path from 1 to 2 to 5, but there's no directed path from 1 to 2 to 5. Okay. Is that clear? Okay. Next, so we'll also use this idea later on, which is the parents of a node. Okay, parents of a node are make sense in a directed acyclic graph. So parents of a node are basically the nodes corresponding to the incoming edges to this node. Okay. So for example, in this graph, there are two incoming edges from A from B. So A and B are the parents of C. Okay. Any questions about this? No. Okay. So yeah, I mean, this further examples. Let's go. Descendants of a node. Descendants of a node are all nodes that can be reached by following the arrow directions from the current node. Okay, those are all descendants of this node. So in the below graph, from A, what nodes can you reach? You can reach C, you can reach D. Okay, because you're following the directed path. Okay, so D and C are the descendants of A, and similarly, descendant of X3 would be just X4. Okay, so I guess the last couple of concepts. What is a connected graph? A connected graph is where there is a path between any two vertices. So you throw 100 vertices, pick any two. Hopefully there's a path. Maybe it's too long, or maybe they're directly connected to each other, but there is a path between the two nodes. Okay, then it's called connected. And otherwise there will be separate components. For example, here there's a graph with two components. Okay, two connected components. Because this node doesn't have any edge. It exists, but doesn't have any edge to these remaining guys. Okay. And tree graph. What is a tree graph? Tree will be important in the next lecture when we do talk about. Subsequent lecture we'll talk about inference. Okay. But what's a tree? A tree graph is nothing but a graph where basically there is no loops. So for any vertex pair, there is only one path between them. So for example, from let's say C to E, there's only one path. Okay, for any two pairs of nodes, you'll see that there's only one path. You cannot have two paths from a source to a destination essentially. Okay, so that's a tree. And of course, if you have two paths from let's say A to F, you have two paths, right? Then it's not a tree. Okay, so that's a tree. That's it. That's the information that we need to understand graphical models a little bit today. Any questions so far? Okay. Okay. So let's talk about directed graphical models, or DPGMs. I think that's what I use. So it's also called a Bayesian network. So how many of you have heard of Bayesian networks? Just one? Few people? Okay. So directed probabilistic graphical models are also called Bayesian networks, but there is not much Bayesian stuff going on. It's about a distribution, so you can always use the distribution as a likelihood function, or do some Bayes update, and then you get a posterior and so on. You can do that, but at the vanilla level, there's nothing Bayesian here. Okay. So what do these directed graphs tell us? As I was kind of repeating several times, they tell us about conditional independence between the random variables involved in that graph. Okay, so why do we care about conditional independence? This example is not very this, I guess, motivation is not extremely good, but we can perform if if random variables are conditionally independent, then it allows us to do easy computations of conditional probability estimations and so on. Okay, and we'll see this idea later on in a subsequent lecture. So here, if you ask me why do we care about conditional independence, of course there's some computational advantage that if things are conditionally independent, you can do something tractably, inference tractably, but you can also encode information about your data. Okay, so as I was saying, condition on okay, so for example, condition on education, it doesn't matter which city the person belongs to. Okay, so so let's say there's a city random variable, there's an education random variable, and this is a job random variable. Potentially you could have prior information, maybe for your this example on the fly I'm making it. So condition on the education level, let's say, the probability of being in some city has nothing to do with probability of being born in some city has nothing to do with probability of taking up a job in some other city. Okay. It could be. So this is all domain knowledge related. So if you know this information, then you can encode that in your in your prediction problem or in your exploratory data analysis problem. Okay. So or the point I want to make is that conditional independence is something which is a form of assumptions about how your features are related to each other, and it's a domain knowledge that you may know as a domain expert, and you should use that information. You should ignore that information. You can always figure out a prediction problem, but then it may take more data to get to the same result as knowing this domain knowledge and actually using the domain knowledge and getting away with good prediction accuracy with less data. Okay, that's the idea. So let's look at joint distribution. So let's start with so the next few minutes we'll try to relate the related distribution with a graph. Okay, that's what we're going to do, and in particular we're going to start with directed graphs. So let's say A, B, and C are random variables. Then the joint distribution between A, B, and C is explicitly written this way, and we know that we can always use factorization. Okay, which means that we can write this joint distribution as a conditional probability times a probability over a smaller set of random variables, right? So this is just a definition of conditional probability, actually, the first step, for example. And this next step is further dividing the second joint distribution between A and B to be probability of B given A times probability of A. Okay. So how many of you are not aware of this? Just a few people. So anybody? So a joint distribution can always be factorized, right? I'm just saying that the probability of, so let's look at the two example case. The probability of x comma y is just the probability of x given y times probability of y. Okay, so this is true. I mean, I can also do the opposite. I can do probability of y given x times probability of x. Okay, and this is just from the definition of conditional probability. So you can think of bunch A comma B as your x and C as y. Then the first step follows, right? So C given x, C given AB times probability of AB. And now I'm saying let's do the same operation in a second, recursively. Then you'll get this factorization. And there are many factorizations you can do. Okay. So I mean, any joint distribution you can factorize. Okay. But factorizations are not unique, right? So I could have started with probability of B given AC and then probability of A given C times probability of C. I could have done something else, right? So, but let's say this is the factorization, P of C given AB times probability of B given A times probability of A. Then the way I'm going to create a graph is as follows. So first of all, I'll create nodes for each random variable. So C is a random variable, there's a node here, A is a random variable, and B is a random variable, 3 nodes. Okay, and then I'm going to think of the C as the child and the things on the right hand side of that vertical line as the parents. Okay, which means that from to C I'll have 2 incoming arrows. Okay, and to B there's going to be 1 incoming arrow from A. Okay, so that's the graph corresponding to a particular factorization. Okay, so I have 3 factors. Factors just means these products, these 3 terms. each term has to have a random variable like of interest, right? The one on the left hand side. So because I have 3 random variables, there will be 3 factors, and with each factor, I know that there's going to be a child and and parents, and that lets me get this graph. Okay, and the graph has directed edges because I'm calling the one on the left hand side the child and the one next to the vertical line, on the right side of the vertical line to be the parents. Okay, and you'll see that there will not be any cycles if you do it this way. Okay, and that's just a consequence of how you're factorizing it. So if you have C given A comma B, then later on you'll not have a given C. Okay, something like that, basically. So is this, given a factorization drawing the graph, is that fine? Any questions? Okay. So let's say now, okay, let's say this was the original graph where I did not, I just had, given a joint distribution, I can always factorize it in some way. I factorize it this way, so I got this graph. Okay. Now let's say if C is conditionally independent of B given A. Okay. So that means that you'll use a notation C perpendicular perp B given A. Okay, this is a short form to say C is conditionally independent of B given A, the underlined symbols. Then basically probability of C given AB is the probability of C given A. Okay, that's what conditional independence means. Okay, this is one way to say conditional independence. There are other ways. Okay, for example, you can also say if C is conditionally independent of B given A, you can also say probability of C given A times probability of B given A. I should have used capital letters, but is the same as probability of C comma B given A. Okay, so given A, just joint distribution just factorizes into the individual probabilities, right? So this is what you probably have seen, but here I'm just saying that if C is conditionally independent of B given A, then if A is if you're already conditioning on A, you can drop B basically. That's what I'm saying. So if you can drop B, then you can drop this edge which used to be there from from B to C. Okay, so we got a different graph basically. Yes.
Why can we drop B?
Because I said let's assume, we started with the point that C is conditionally independent of B given A. So that means that P of C given AB is P of C given A, and if you look at the previous diagram, C given AB, we'll just drop B, and so B is not a parent of C anymore, so we'll drop it. Any other question? Okay, so
in the last
yeah,
in the last time there won't be any connection, right? C conditional independent of B, conditional independent of A.
Oh no, so that was not conditionally independent of A. This is the given A. So I just wrote the same thing as what we wrote here, and I said this is the same as equal to this statement. You'll not see C conditional independent of B given conditional independent of A. Okay, that's not clear what you're meaning there. Yeah. Any other question? Okay, so there's going to be so you'll see that actually so in the previous 2 slides I was showing that, okay, given a particular factorization, there's going to be a graph, right? We just saw, like, given the factorization and a conditional independence assumption, a graph changed. Okay, but there is no one-to-one relationship between a factorization and a graph. Okay, that's what I want to say in the next couple of slides, which means that for the same factorization there could be actually I should say, yeah, for the same factorization there could be multiple graphs. Okay, in the sense, all I'm trying to say is that looking at the factorization you can always draw a graph, but you could also potentially draw some other graph as well, and we'll understand what that means here. So let's say there are n random variables and there's a graph G. So the way we're going to relate the graph and the distribution over these random variables is that maybe x respects G is just phrase they use, or the distribution respects the graph if the distribution factorizes according to the layout of the graph. Okay, if the distribution factorizes according to the layout of the graph, then that distribution respects that graph. Okay, this is kind of natural, right? If literally this thing is exactly product of xi given parents of xi and so on, then you can, and if the graph literally is about xi connected with the parents of xi being exactly them, then that's fine. Okay, but the ambiguity comes from the fact that the graph, this non-uniqueness comes from the fact that the graph does not imply that the random variables are conditionally dependent. Okay, by which I mean, if I draw, let's say this is B and this is A, if I draw an edge like this, doesn't, if I draw the graph like this, okay, doesn't mean that the random variables A and B are conditionally dependent or dependent in general. Okay, so I could put down something else and say condition, but just drawing an edge doesn't imply that A and B are related. Okay, we can only talk about A and B being independent given something else, but we cannot say by looking at edges that A and B are actually correlated or essentially. Okay, if I put an edge, so if I have a graph, I can put all sorts of edges, right? So let me put an edge from, let's say, C, edge from C to A. Let's say this is the graph. Okay, this doesn't mean that C is correlated with B, C is correlated with A, and B is correlated with A. Okay, in the sense that presence of an edge doesn't mean much, but the absence of an edge can mean something. Okay, that's the non-triviality. Absence of an edge, we saw that, right? We saw if things were conditionally independent, we could, there's an absence of an edge. Okay, but the presence of an edge doesn't imply dependence. That's what the statement is saying basically. Which means that the graph does not uniquely determine the probability distribution P. Okay, which means that for the same graph there could be several different probability distributions. Okay, so actually I should say non-unique, instead of non-unique graphs I should say non-unique distributions for the same graph rather. Okay, for the same graph there could be multiple distributions. Okay, why is that? I don't know if I have examples. Yeah, I have examples. So let's go through the example. So let's say A, B, and C are independent. Then the probability of A, B, and C is just the probability of A times probability of B times probability of C, right? Actually, I'm abusing notation a little bit. So probability of A, B, and C is actually a table, right? So let's say A, B, and C are binary random variables. Then you have a eight number of rows. Number of rows is 8, and for each realization 0, 0, 1, 1, 0, 0, and so on, there's a probability score, number between 0 to 1. But here I'm abusing notation, capital letters and lowercase letters. So A, B, and C are independent if this is true actually for all choices of A, B, and C, and let X is the set. Then let's say the graph is like this. There's a graph A, there's a graph B. Node A, B, and C with no edges. Okay, this is a graph with no edges, but 3 nodes. Okay, so this graph exactly captures because there's no parent of A, no parent of B, no parent of C. It captures this, right? This factors. It's fine. Okay, but this distribution, independent distribution, also respects any other graph as well. In particular, for example, this graph. Okay, why is that? Because this graph, from this graph, all I can say is maybe there's a factor P of C given A comma B, and there's a factor P of A, and there's a factor P of B. Okay, that's all this graph is saying. It's not further saying that P of C given AB is actually P of C. Okay, that's a nuance, right? So from looking at the graph, I cannot say anything about dependence structure. Okay, so but I can say something about independence structure. Okay, so actually we'll see a couple of slides that in this graph A and B are independent. Okay, that you can see that random variable A has not taking a value has nothing to do with random variable B taking a value, because if they take a value, let's say they're binary, you can flip a coin A, flip a coin B, and then maybe their values may influence C, okay, but they themselves are not influencing each other. Okay, but we'll make that concrete in the next slide. But here all I want to show is that for this distribution, the independent the independence assumption across random variables, you can draw any graph, because the graph is all those graphs are consistent with the this factorization, because once you draw the graph you may have some factorization and then you can drop these guys because of that independence, and then that's true. Okay. Yeah, so yeah, I think I just explained. G is not saying that C depends on A and B. Okay, so this is the crucial point. Dependence is not being explicitly stated by the graph. Independence is what the graph will tell you. Okay, and independence and dependence, it's not like exact negations of each other. Okay, from the graph at least. I mean, in general, yes, but yeah, I mean here I'm saying that even this graph also that distribution also respects this second graph. So the right way to say this is that this distribution, or P respects G, this particular distribution, which is the product distribution, respects this graph, and respects this graph. Okay, this is the terminology. Okay, any questions up to this point? Okay, so let's look at an example. So there's a version of linear regression called Bayesian linear regression, where basically you assume that the parameter is also a random variable. Okay, and yeah, the parameter is a random variable. In particular, the parameter is, let's say we assume that it's normally distributed with let's say it's 10-dimensional regression problem. Then W is 10-dimensional random variable with mean 0 and some covariance matrix, and each of the yi's are also random, normally distributed, but with mean being the value that the first random variable took transpose some transformation of features, right? Phi of xi is, think of this as just x for example. Phi I just added because you can transform the input raw features into other things, right? With that mean and some variance. Okay, this is yi is, let's say, is a 1-dimensional random variable. Okay, so let's say you're predicting one value which is let's say temperature given other features like previous temperature values and other things. Then it's one number. So yi is one number, but we are saying that that is normally distributed with some mean, okay, and some variance sigma square. The mean involves some features phi of x I for this particular ith observation, transpose w. W is this weight or the linear coefficients, and the linear coefficients themselves are normal. Okay, so that's the assumption. So what is the contrast with the original linear regression? In the original linear regression, you would say W is some fixed unknown vector, okay, that I'm gonna predict. So that I'm gonna estimate using training data by let's say minimizing least squares loss, right? Instead of that fixed unknown vector, I'm saying now the W is the weights are, or the coefficients are random, okay, and they're Gaussian. Okay, actually you must have seen this when you're doing ridge regression. Ridge regression is like a Gaussian prior on the coefficients and then a Gaussian assumption on the observations. Okay, I mean literally this Gaussian assumption on the coefficients, Gaussian assumptions on the coefficients gives you gives you a product of these normals, and if you, that's the likelihood. So you will get a, okay, if you do a map or maximum a posteriori estimation on this model, then that will give you an optimization problem which is the same as the ridge regression problem. Okay, just as a tangent, but for now W is a random and yi's are random, and the graph corresponding to this would be something like this. So where yi's are y1 to yn is the number of observations you have. Okay, there are n observations, let's say 1,000 observations, 10,000 observations. They're all, those observations all correspond to random variables. Okay, those random variables are not independent. There are some edges. Okay, there's an edge from a random variable which is W to each one of them. So clearly there's at least a path, maybe not a directed path, but there's a path between each of these observations. Okay, but you'll see that given W, all these observations are independent. That you can see. Like given, let's say fix a value of W, then each yi has nothing to do with other yi. Okay, so they are conditionally independent of each other given W, but they are dependent in the general graph. Okay. Yeah, I mean, what is the consequence of this dependency is that if you see, let's say y1 to y50, then it should tell you what is that should inform you what the random variable w could be. I mean, what is the value that let's say you did not observe w, I mean, which is definitely you don't observe w anyway. Let's say you did not observe the next random variables as well. Knowing the previous random variables values can tell you what the unobserved random variables are because of this dependency. Okay, if things are independent, you can't, given a first coin flip, you cannot say what the second coin flip is. But if things are dependent, you can say what the second coin flip could be. Okay. Yeah, so this is just what I mentioned. So the joint distribution between the weight vector and all the observations is in this product form, factorized form, and this is the diagram that this is a plate notation where I put all the yi's in as a single yi and put a box around it that there are n copies of these random variables. Okay. W is called a hidden or a latent variable. Okay, because we don't observe w, and yi's are called observed variables. Okay. Any questions about this? Yeah.
W is a distribution.
W is a random variable. Yeah.
You said it's Gaussian.
We assume it's Gaussian in this this linear regression example. Yeah.
So the y that will be the outcome of the y is that will be the outcome of the group. So
yeah, y is related to w. So think of it as like the generative process. Remember LDA, I said start with the topic distribution and then you get the actual words which are also random, right? Here you start with w, sample a w, and then fix the w and generate all these observations. Okay, that's the generative view of this this modeling framework. Okay.
with one particular fixed w, we are getting different observations.
Yeah. Otherwise, you would have multiple copies of w. So there's only one w variable here. Yeah. Otherwise, I would have said y, wi, wj, and so on. Okay. So you'll see this notion latent or hidden random variables several times, and you'll also see observed random variables several times. So in the hidden Markov model, those random variables at the top of that that graph were hidden, and random variables which are at the bottom were not hidden. Okay, observed. That's why it's called hidden Markov model. Okay, so here's another example. Okay. Let's see. So here there are 5 random variables. Okay, 5 random variables which are written here: difficulty, intelligence, grade, SAT score, and letter. Okay, and given yeah.
So independency doesn't mean that there are 2 variables uncorrelated. Is it true?
Yeah, independence implies not correlated, right? Yes. Why are we talking about correlation? What is it?
Independent of the distribution of the random variables.
Yes. No, I don't understand your question. What is meant by independent?
So independency means uncorrelated. Okay.
Yeah, independence implies uncorrelatedness. Correlatedness is just a second moment property, essentially something like covariance or something. Okay, or normalized covariance. So if things are independent, definitely they are uncorrelated, but uncorrelatedness doesn't imply independence, except for Gaussian distributions. Okay. So what I'm trying to do here, the first example was a particular linear regression model. The second example is a stylized example. This is a network of 5 random variables. Okay, and there is actually domain knowledge here, that we are saying that difficulty and intelligence both lead to a grade. Okay, and the grade leads to a recommendation letter or maybe an award letter or something, scholarship letter. But only intelligence influences the SAT score. Okay, so some sort of, actually you can think of this some sort of a causal assumption I'm making here, but this is domain knowledge. Okay, so that's an example of a network. So here I'm really embedding domain knowledge. So you can talk about independence conditional independence ideas here. For example, grade and SAT score are conditionally independent of each other given intelligence. Okay, fix the intelligence, grade has nothing to do with SAT score. So if somebody gets grade A or C, has nothing to do with how much SAT score they're going to get. Okay, that's the assumption being made in this model. Okay, and we'll see these independence more systematically later on. But in this example, there are 5 random variables, and you know that this is the general form, right? For each random variable, there will be a factor. So this product form says for each random variable in my, each vertex in my vertex set, in my nodes in my graph, there has to be a probability of that node given its parents, right? That's the general form for the Bayesian network, right? Or any factorization. And in this case, there are 5 random variables: D, I, G, S, and L. Okay, just the first letters of those random variables, and we are explicitly saying from that graph we can say it's probability of D times probability of intelligence times probability of grade given intelligence and difficulty times probability of SAT score given intelligence times probability of letter given grade. Okay, so that's the factorization here. Now, what are the parameters in this model? Okay, so those are given by these table-like things. These are probability tables, right? You must have seen this in some previous classes. So this is literally saying for every value that this random variable takes, tell me what is the probability score associated with it, with that value. Okay, so intelligence takes binary values, intelligent and non-intelligent, maybe intelligent with some probability, and not intelligent with some other probability. Those are 2 numbers. Okay, so these are the parameters of this joint distribution, and this is the factorized version. So the graph is this is the graph which encodes the dependent structure, and this is joint distribution factorization. Okay, I mean, how did we get these numbers? How did we get this graph? Those are all good questions. Okay, those will be related to the learning problem. Like, given a bunch of random variables, what is the graph relating them is a learning problem. And even if you knew the graph, how do you know, like, what is the parameters of the random variable itself is also a learning question, right? If I say all these are normally distributed, you have to tell me what the mean and the covariance, mean and the variance are, right? So that would be the learning problem. Okay, inference problem would be, given that I told you that somebody maybe the difficulty level is for a course is pretty high and intelligence is pretty high and SAT score is pretty high, tell me what is the probability that this person is going to get a grade B or A. That's an inference problem. I'm asking condition on some other random variables taking some values, tell me what is the probability that this person is going to pass or fail, right? That's an inference question. And there's another example, we'll skip it, but this is from a paper from like 2 decades ago. Okay, so here they're really encoding the some sort of domain knowledge, like maybe the starter is only going to influence the engine cranks, and only radio is only going to get influenced, but will not influence whether the car will start or not, and so on. So there's a lot of domain knowledge, right? This type of domain knowledge you will not be able to encode in other frameworks, like in a deep learning network. How will you encode this domain knowledge? Maybe you'll have indicator features of things, but how will you say that one leads to the other, or one is conditionally independent of the other? It's not clear. So now let's look at 3-node graphs. For the next 3 slides, we're going to look at 3-node graphs and try to read off conditional independence. So I was telling in the previous slide, I directly said given intelligence, SAT score has nothing to do with a grade, right? So how did I say that? So let's actually look at it. Oh, but we'll take a break. We'll take a break for 8 minutes and resume at 7:40. Okay. Okay, so let's resume. We're going to look at 3-node graphs, which are really simple, just 3 nodes, right? 3 random variables. But that will give us a good idea of how to talk about conditional independence. Like, we can read the conditional independence directly here. In fact, there's a reason why I drew the A and B in blue and C in green, because C is the random variable on which we are going to condition on. So given C, let's say C takes a value something. Given C, we in fact this slide is trying to say that A and B are independent. Okay, so and for 3 nodes it's kind of easy to see that. So probability of A, B, and C, let's say it factorizes. So this factorization respects this graph, right? So because A's parent is C and B's parent is C, right? So That's what we wrote. The two factors for A and B are this, and P of C itself. Now, if you condition on C, what is the conditioning on C? By just the definition of conditional probability, probability of AB given C is probability of A, B, and C divided by probability of C, right? And then probability of A, B, and C, we can just use the graph's factorization as substituted here, and you can see that probability of C and probability of C in the denominator cancel. So you can see that probability of AB given C is probability of A given C times probability of B given C. Okay, that means that A and B are conditionally independent of C, so conditionally independent of each other given C. Okay, so that's the statement. So I'm just saying that in this graph with the edge essentially going outwards. Okay, so now just looking at the graph, edges going outwards for this three node graph imply that given C, A and B are conditionally independent. Okay, so you can see that, I mean, in the linear regression case there was a single W and there were a bunch of Y's, Y1 to Yn. Given W, all these observations are independent. Okay, but without knowing the W, these observations are related to each other. Okay, so if I know the value of Y1, I'll have some posterior, I mean, conditional probability of what Y2 could be. Okay, some information flows through W. Okay, so is this example clear? Because it's a very fundamental example. Okay, so next is a slightly similar graph where the edge from, instead of an edge going from C to A from the previous slide, it's going from A to C. Okay, it's like a flow. I mean, it's like a path where it's going from A to C and C to B. Those are the two directed edges. Okay, even in this case, it turns out that the conditional probability of AB, so probability of AB given C is just a product. Okay, it's a product of probability of A given C times probability of B given C. Okay, so even though I change the direction of the edge from C to A to C, the conditional independence property still holds. Okay, that you can see. So this is just a definition from the graph, and then we do some manipulation. Basically, we write it as probability of A times probability of Z given A is probability of A given C times probability of C. Okay, so that's this underlined portion, and this portion we do some manipulation. Okay, and with that, if you divide by C, then you can see that this thing goes away, and probability of A given C and probability of B given C. Okay, so for 3 node graphs, we can read off what is conditionally independent, which variable is conditionally independent of which other variable given some other random variable. Okay, so those are the two easy ones. There's another slightly interesting one, more nuanced, which is this graph where C has two parents, A and B. Okay, C has two parents, A and B, and actually in the causal inference parlance, this is called a collider. Okay, some name, collider, but anyways, for us it's just a graph with 3 nodes, and the C is the child and A and B are the parents. Now, condition on C, we cannot say that A and B are independent. Okay, in this example. Okay, because you cannot really manipulate. So this graph has a particular factorization structure, right? Probability of A times probability of B times A and B don't have parents, and probability of C given AB, right? You cannot really massage, in any way to get probability of AB given C as probability of A given C times probability of B given C. You cannot do that. Okay, so because we are not able to do that, given just this information, we cannot say that A and B are conditionally independent given C. Okay, yeah. So here is an example. This is like grounding the random variables a little bit. Let's say A is a Bernoulli random variable with bias 1/2. Okay, this is a Bernoulli random variable, coin flip, and this one is also a Bernoulli random variable, which is coin flip. Okay, and let's say C is a derived random variable which takes a value 1 if both the coin flips are if both the coin flips are heads or tails, and 0 if one is heads and one is tails. Okay, right? So now, condition on C, if we know A, then we know B, right? Condition on C taking a value 1, if C took a value 1, we know that both are supposed to take the same heads are heads, tails are tails. So if I know what the value of A is, then I know what the value of say B is. Okay, so that's all I mean. They are dependent. Okay, and so we cannot say that A is conditionally independent of B given C. By just reading the graph, it may be the case that they are actually conditionally independent, but from the graph we cannot infer that they're conditionally independent. Okay, that's all I mean. Now, but this is the second interesting property. Okay, in this graph, actually A and B are just unconditionally independent. Okay, so that conditionally we cannot say whether they're independent or not. Okay, but unconditionally A and B are independent because A has no parents, B has no parents. Okay, and you can just manipulate. So P of A comma B, so even without manipulation, you can just look at the graph. So A doesn't have any incoming edges, so nothing to influence this guy, nothing to influence the other guy. So them taking any values is not constrained by anything. Okay, because C is not in the picture. Okay, I'm just asking unconditionally if A is independent of B, then they are. Okay, flipping the first coin with a bias of 1/2 has nothing to do with flipping the second coin as well with a bias of 1/2. But given if I tell you that I've observed C value and it's 1 or 0, then they are dependent. Okay, those two random variables. Okay, and here is just a simple manipulation. Probability of A comma B. I can always introduce a third random variable and sum over it. Okay, this is a important trick that you should remember, that if you have a joint distribution, you can always add some additional random variables and marginalize, only to see if it makes your life easier. In this case, if we add all three, we have this identity, right? We given the graph, we have this probability of A, probability of B, probability of C given AB, and then these two have nothing to do with A and B. Nothing to do with C. So you push the summation inside, so you have this summation, and we know that sum over all the values of the left hand side of a probability distribution sums to 1. So this is probability of A times probability of B times 1. Okay. So that's just a algebraic way of trying to show that A and B are independent. Okay. Any questions? Is it too? I'm going too slow. Okay. Okay. So this is a summary for the three node graphs. So the only thing changing between the 3 node graphs is the edges, right? So edges going outside or edges going in a path type of a fashion, they are fine. They are conditionally given C, A and B are conditionally independent. But for edges coming into a node, okay, given C, A and B, we cannot say they are conditionally independent. Okay. So those are the information that these graphs are implicitly capturing. When I drew this graph between the A, B, and C, I am implicitly capturing that, essentially these properties. Okay, and this we cannot really say anything, so it's really not capturing anything. I mean, it's capturing something basic, right? A is independent of B. That's it. Okay. Now, why did we look at 3 node versions? Because we'll now go back to the basics of graphs. There is the notion of paths, right? Paths. We look at paths. They could be complicated, but we'll look at 3 nodes at a time. And 3 nodes at a time, we can look at the kind of base our intuition from this and understand whether on those paths, something happens, conditional independence property holds, and therefore we can say something about bigger graphs, okay, about conditional independence. So there's a formal way to do that. So let's say we have a general graph, n nodes, okay, and which is a larger DAG. So the same idea. So in the previous slide with 3 nodes, we explicitly derived what could be conditionally independent or not, right? Here we'll look at the general idea of d-separation. It's an idea which will directly let you figure out, given an arbitrary graph, directed graph, it can directly let you figure out whether some bunch of nodes are conditionally independent of some other bunch of nodes given some other nodes, okay, most generally, okay. And if you are getting, like, why are we doing this? Just think of that, SAT, intelligence, difficulty graph. Okay, somebody must have, come up with that graph structure. Okay, so somebody, if they have come up with that graph structure, we are already assuming that given intelligence, SAT score has nothing to do with the grade. Okay, So we need to infer that. So somebody designed that from data or doing experiments and gave us a graph that's already implicitly encoding some information, metadata, right, about these random variables or these features. Okay, it's kind of critical in causal inference type of settings, and also useful in our machine learning like LDA or any of these methods. So that's the idea. So let's see. So deseparation. So we have not really increased the number of nodes. We've increased it to 5, but it gives us the idea. So what is the idea of deseparation? It lets us read off conditional independence properties from any graph, okay, from any directed acyclic graph. So let's say the sets of random variables now, they are not single random variables, but sets, okay. So in this example, the set is the blue set is going to be the set B, the green set is going to be set C, and this orange set is going to be set A, okay. The 3 sets of random variables, okay, and they're disjoint, and they don't have to cover all of the graph, okay. There could be some nodes which are not in this 3 sets, okay. Now we want to ask a question, by just looking at this graph, not just looking at this graph, but can we ask the question whether A is conditionally independent of B given C? Okay, that's the question. Is the set A conditionally independent of set B given set C? Okay, so that's the question. That's the type of question we can answer by doing some mechanical operations. And the operation, to do the operations, I want to define what is deseparation. Okay, so to define deseparation, there's also another more elemental property, which is for a single path, I'll say something about it being blocked or not. Okay, so we'll start with whether a path is blocked or not, and if like something like all paths are blocked, then there is some deseparation, and if there is deseparation, there's going to be conditional independence. Okay, so let's at the basic level, there's a path, right? There's a path between all these random variables in set A, B, and C. So let's understand what can we say about the paths themselves. So a path is blocked with respect to set C. Okay, so the C is the one we're conditioning on, right? Given a set C, we want to say there's a bunch of random variables A, there's a bunch of random variables B, and there's a set C in between. Let's say, forget about the graph over here, there's a set C in between. There'll be a bunch of paths, right? So we don't know how many paths there are. Let's say there are 3 paths. Okay, I'm saying that pick one of these paths. Okay, and we're going to say this path from the vertex in A to a vertex in B is blocked. Okay, with respect to this set C, if it passes through a node V. Okay, if that path has a one of the nodes on the journey on the path is a node V, and V belongs to C. Okay, where V is in C. Okay, let's say there's a V. Oops, I don't know how to get rid of that. Okay, so let's say there's a V in C. If V belongs to C and the arrows on that path are head to tail or tail to tail, by which I just mean that there's a path, right? So from a vertex VA, some vertex in A, so some vertex in B, there's a vertex V, okay, which is in C. Let's say if the arrow direction for that, it's on the path, so there's a particular path. If the arrow direction is like this, okay, coming from some 2 other nodes, doesn't matter. If it's just like this, then it's a head to tail type of this is what we studied in the previous 2 slides. Okay, oops. Right, if the arrow directions are like this, or the arrow directions are and the remaining path like this, if the arrow directions are like these, then that path is blocked. Okay, condition on C, that path is blocked. That's all we mean. The second part is taking care of some edge cases. So let's not worry about the second part, but this is again a mechanical thing that you can do. The first part is just saying that given V, if V is on the path, given V as in given C, therefore given V is on the path and the directions are exactly what we analyzed for the 3 node case, then that path is blocked. Okay, any questions? Who's not following what's happening? Yes, question then. So do you understand why we are studying deseparation? the 3-node case, we could just do some manual calculation to see if given C, A and B are independent or not. Okay, and even to motivate that, I said go back to that slide with intelligence and SAT score and just see that okay, somebody gave you that graph. It implies already conditional independence assumptions. So can you read those conditional independence assumptions off from that graph if somebody gives you that graph? Okay, somebody learned that graph using data. Okay, and then they give you that, and then say given this graph, I can infer if somebody gets a high grade whether they are intelligent or not. I can do that. Okay, given the grade value, I can tell you what is the probability that somebody is intelligent or not, right? Because I know the joint distribution, right? So somebody gave you that graph, and what the subsequent exercises have been just to understand, okay, what assumptions are they making when they created this graph or when they derived this graph from data. Okay, and that's what we are doing in a general fashion. So first we touched 3-node graphs because it's easy to do manually whether conditional independence holds or not. And for the n-node graphs, we are just invoking rules. Okay, and the rule is called deseparation. And for deseparation, we need to understand only one thing, which is the notion of blocking a path. Okay, so we're going to look at sets of random variables A, B, and C, and basically think of this type of a picture, maybe not the one below, but this type of picture here, 3 sets. Okay, and you just want to see, okay, those 3 sets, there could be many random variables in set A, many random variables in set B. Okay, think of just a graph. There could be many paths between them from A to B. Okay, conditional independence just means somehow we block all these paths. That's conceptually what we're doing. Okay, and hopefully if the paths are like this, the circled ones that I drew below, then, and if it's true, so pick all the paths, pick a variable in set A, pick a variable in set B. Okay, there's going to be potentially a path between them. If that path is blocked, that's great. Pick another variable, maybe pick all pairs of variables, all the paths, look at all the paths. If all of them are blocked, then it's conditionally independent. Okay, that's what we're going to get to in the next slide. But here I was just showing that if these conditions hold, then it's then the path is blocked. Okay, and there's a second condition as well, but it's a fringe case condition, which is basically saying that if there's a v which is not on the path, if there's a v which is on the path, but it doesn't belong to C, but its descendants also don't belong to C, then there is some path blocking. Okay, so, and also they have to be head to head. Okay, so there's several conditions, but let's not worry about the second point. The first point is at least natural and covers a lot of cases. Okay, second point is also very important, but don't worry about it. So in this, so in that example on the right side, we're saying that given x3, we're asking whether x2 is conditionally independent of x5 and is x4 conditionally independent of x5. Okay, those are the 2 questions. Okay, if you look at just the path from okay, here we're really not talking about, so here we're really talking about okay, let's say go to the now here, because B, x4 and x2 belong to B itself, so okay. So let's look at this path from x2 to x3 to x4 to x5. Okay, there's a path, right, between set B, the one variable in set B, which is x2, and some variable in set A. There's only one variable in set A, so x5. Okay, so there's one path from there because this is a tree graph, and you can see that because V is in C, V is x3, and it is in the in that, what is this called, head to tail configuration. So that path is blocked. Okay, so that path is blocked, but you will see that x4 and x5, there is no path blocking because they are directly connected to each other. Okay, so there is no C that blocks them. So one path is blocked, one path is not blocked, so we cannot say whether A and B are conditionally independent of C. We cannot say that. Okay, that's the conclusion, I mean, which I think we'll see in 2 slides. Okay, so this slide was just talking about a basic thing, which is path blocking for every path, whether it's blocked or not, and deseparation. 2 sets are deseparated, or essentially it's a, I don't know why we are distinguishing between deseparation and conditional independence, but let's say 2 sets of nodes are deseparated by C if all paths from vertices in A to vertices in B are blocked with respect to C. Okay, that's the diagram, right? So I drew a I drew a B. All paths from A to B are blocked by set C. Okay. And if A and B are D separated by C, then A is conditionally independent of B given C. Okay. Any questions at this point? Let's not go into the details of necessary and sufficiency. It's just something technical. Okay, so this is the same example from before. So it's the same, set C, A is here, and B has 2 nodes in it. Okay, so to say that whether the set A has anything to do with the set B, which is these 2 nodes, you want to check 2 paths, right? So there's a path. So pick a vertex x5, and you have 2 choices: x5 versus x4, x5 versus x2, 2 pairs, from one from A and 2 from B, so 2 pairs. So there's a path from x5 to x4, and there's a path from x5 to x4 to x2 as well. Okay, so there are 2 paths. Okay, there are no multiple other paths, so there are only 2 paths I need to check. One path we just saw that it is blocked. Okay, but the other path there is no blocking, so we cannot say that A is independent of B given C. Okay, so I guess this is a negative example. I could have shown you. I could have put another node over here, and I could have said that both paths are blocked, so A is conditionally independent of B given C. Given C, right? I could have shown that, but that's how you do a calculation for d-separation and for in general for general networks. Okay, you pick every pair of nodes from A and B and see if it's blocked or not. And the blocking condition we just saw 2 slides ago. If all paths are blocked, then it's d-separated and therefore conditionally independent. Okay. So here is another example. Here I just changed the A from x5 to x1. Okay. Now you can see that condition on C. Okay, let's look at 2 paths. So x1 to x4 and x1 to x2. Those are only 2 paths, right, in this tree graph. And so for the first one, x1 to x4, it does go through. There is a node in C, and it goes through. It's on the path, but it's in the head to tail configuration, as in going in, going out. So x1 and x4 are conditionally the path from x1 to x4 is blocked by x3 or a node in C. But if you look at the path from x1 to x3 to x2, these 2 nodes are in the what is it called, head-to-head configuration. So C is like is not on those 2 nice conditions. Okay, so condition on C, sorry, not condition on C, but you can check the path blocking condition to see that x1 and x2 are not blocked by the node in C. There's only one node in C, so they're not blocked by that node in C. Okay, so the element on the path, either it has to be only in the head-to-tail or tail-to-tail configuration, or that element on the path should not be in C and its descendant should not be in C. I think that was the second condition. In this case, the only element on the path is in C, right? So there is nothing else we can do. So that's why the path is not blocked by C, and therefore even in this case, A is not conditionally independent of. We cannot say whether they are conditionally independent of B given C by just looking at the graph. But maybe in reality, I said each graph can correspond to multiple graphs can correspond to the same joint distribution. Same joint distribution. So maybe they are independent, but from the this graph we cannot infer that they are conditionally independent or not. Okay. And so is the example clear? So I just moved from why conditional independence is interesting through that student network example to 3 node graphs to general graphs. Okay. Actually, conditional independence also, let me make a remark that it is very important for causal inference. So if you're trying to you got some data. So typically in causal inference, you either have to run an experiment like A/B testing or some what is called a randomized control trial, or you could get observational data. You measure some things in a system, and then you're asking whether if I now purposely did something like bring an intervention, give some drug to a patient, or give some shock to the system, as in like make some intervention, then you're asking whether what is the effect of that intervention on some variable of interest. To figure out whether you can do that, you'll actually have to figure out whether things are conditionally independent or not. Okay, so conditional independence, these properties that we're studying, is also a subset of a bunch of things that you need to do even in the world of causal inference. Okay, although we are not going into that world here. Okay, here it's our interest is what domain knowledge is it encoding a graph, and subsequently we'll see that it's useful for inference and learning and so on. Okay. Okay, so I'm going a bit slow. So yeah, okay, so I don't think so some minor points there. So I mean, I guess worth repeating, represent independence, not dependence. And one, I guess, last slide for directed probabilistic graphical models in terms of representation is that if you have a joint distribution bunch of random variables, and if you assume a graph, somebody gives you the graph, okay, that graph is basically, initially you don't know how all random variables are related to each other. So there could be many joint distribution factorizations. Think of factorizations of these distributions. Given the graph, it kind of reduces the number of factorizations of that those random variables can have. Basically, it's shrinking that set. It's like a constraint on the set of distributions you have. Okay, that's what I mean by filter view. Okay, and there are some examples here about non-uniqueness that we discussed several slides ago. So, and a minor point about continuous distributions, A, B, and C, you don't have to think of them as discrete distributions or just Bernoulli trials that we saw in the examples. They can be continuous as well. Okay, and in fact, those random variables need not be variables themselves; they could be vectors as well. Okay. Any questions about directed graphical models? Now I'm gonna shift the gears and talk about undirected graphical models. And you may say, okay, why am I thinking about undirected again? Undirected or directed? The short answer to that is that some conditional independence assumptions cannot be captured in using just directed graphical models. Okay, and we'll actually see an example towards the end. In 10-15 minutes, and yeah.
Could you again explain what happened in the head-to-head case and the conditional probability?
Here. Oh, I mean here or in the smaller one?
Yeah, in this.
No, here we are just executing. Here we just have to check two things, right? So the set A is given, set B is given. Okay, set A only has one vertex, set B has two vertices. So we just have to look at two pairs of nodes, right? x1, x2, and x1, x4. Okay, so x1, x4 clearly given C, 1 and 4 are blocked. Okay, that path is blocked. But for x1, x2, the path is not blocked. Okay, why is that? We just have to look at that definition of path blocking. So first of all, the path is such that there's only one node, one vertex on this path, one additional vertex which is not in A or B, which is this one, x3, and that V belongs to C. Okay, and if V belongs to C, we only know that if it belongs to C and it is in the either this configuration or this configuration, then it is blocking the path. Okay, whereas here the edges are going in. Okay, so edges are going in, and V belongs to C is a situation which was not covered in the blocked case, so it has to be in the opposite case, which is not blocked. Okay, so it's not blocked for these two. So in general, so at the moment any one path is not blocked, those two bunches of random variables are not conditionally independent of a given C. Okay, which means, so what is the consequence of that? So which means that if you know some values of some, let's say set A, that has influence on what values set B can take, even if you know the value of C. Okay. Okay. So now I was just saying that some conditional independence properties cannot be captured by directed ones. So that's why we are looking at undirected ones. Okay. And the undirected ones are easier. So that's why I've kept it for the last. We went through the tougher material first. So undirected graphical models are also called just Markov networks or Markov random fields. Okay. You might have seen these names somewhere potentially. So it's just called Markov random fields. Okay. Or Markov networks, just like Bayesian networks for the other guy. And there are no edge directions. And again, the whole point of these graphs is to capture some conditional independence properties. So what are those? Okay, so what are those? So we'll directly look at it. So there'll still be factors. Okay, same factors like we saw in the directed probabilistic graphical model. There's going to be factors, terms involving each involving these random variables, the nodes, right? But these are called potentials, and they need not be a conditional probability. So remember the factors in directed probabilistic graphical models, each one was like A given BC or B given C in that version. Okay. Here we are not going to say that they are conditional probabilities. Here they are just going to be some functions of sets of random variables. Okay. So for example, probability of A, B, C could be a product of two functions, where one function is has only arguments A, B, and the other function is the arguments B, C. Okay. I mean, of course, these functions could be probability of A given B or probability of B given C. It could be, but in general, I'm saying that there could be any function. Okay, and if there are any functions, they may not be even between 0 to 1. So I have to normalize this distribution such that the joint distribution sums to 1 if I do the summation over everything. Okay, that's why I've added this additional guy Z. Okay, so that's the that's basically the factorization imposed by a undirected graphical model. So let me tell you what that I mean. At this point, you're saying, okay, where is the graph, right? I just wrote some two terms with two arguments. So where is the graph? So here's the graph. Okay. So if the graph is, let's say 3-node graph. So if the nodes are A, B, and C, then I am gonna look at, for example, one clique A and B, the other clique B and C, and I'm gonna write two functions, phi of AB and phi of BC. Okay, that's I'm just driving the intuition that given the graph, what is the factorization that I'm thinking about for my joint distribution? It's going to be like this. Okay, phi 1 of the nodes involved in that clique and phi 2 of nodes involved in that clique. Okay, and phis are just functions. We are calling it potentials, but they're just functions. Okay, non-negative functions. Probabilities have to be non-negative, right? And so in general, so undirected probabilistic graphical model is basically defined as basically the way it captures the joint distribution is a product of potentials, or these basically functions, over cliques of the graph. So given a graph, just figure out what all cliques are there. I mean, at the minimum, you will have edges as cliques, right? You have many cliques in a graph. At the minimum, every edge is a clique. Okay, every edge and every pair of nodes is a clique. But look at all the cliques and have a term involving each clique. Okay, that's a factorization of the joint distribution. This may not be the minimal one because you can always pick biggest cliques, or you can have redundancy and all that, but that's fine. So bunch of cliques, that's the set of cliques C, and for every clique there's a function, okay, where xc represents the bunch of random variables related to that clique, or a bunch of nodes related to that clique. Okay. Okay, don't worry about the special case part. So here's an example potential for a 3-node graph. Okay, let's say the 3-node graph is a complete graph. So how many cliques are there? No, there's a one big clique, but there are 3 more cliques, right? Every pair of edge, every edge is a clique. Okay, so 3 cliques plus one bigger clique. So either you can say, okay, the joint distribution imposed by this graph is either just P of A comma B comma C, that doesn't say much, or you can say there's factorization like this. Okay, and here I've explicitly written what those functions are. So if A takes, so let's say A, B, and C are binary random variables, then A taking a value 0, B taking a value 0 is some number which is definitely not less than 1, right? And A taking a value 1, B taking a value 0 is some other number. So I'm just saying that for every pair of, what is the function? For every pair of inputs, I'll tell you what the output is. That's what these tables represent. Okay, and you can see that some of the numbers are greater than 1, but that's fine because I have this additional z, which will ensure that this thing is actually a distribution. Okay, in this case, you sum over every all the values that these products can take, and that's something. It's such that now this guy is a distribution. Okay, that's all. Okay. Marginalization is not very critical. Let's go to conditional independence. So in a 3-node graph, okay, something like this, there is no edges. Okay, there's no the 3 variations that we had. In this 3-node graph, conditioning on B makes A and C independent. Okay, so if a graph is like this, if I give you B, then that guy is not random anymore. So that kind of severs the path from A to C, and A and C are independent given B. Okay, so how do we, why is this true? You can actually use any, so here there are 2 cliques, right? So phi of AB, phi of BC. Okay, you can actually do all the summation to see that you will get essentially a function of actually, since it's 2 clique, literally there's a function phi of AB and phi of BC. So it just follows directly. Okay, but what about bigger graphs? Okay, in the bigger graphs also the scenario is quite simple. Okay, there are 2 ways to look at conditional independence, how to infer conditional independence. Okay, one is called the global Markov property, and all it says is that think of 2 sets, and in this case I'm going to draw it in a very suggestive way. So let's say set A, and there's another set B. Okay, and there's a set C. Okay, if all the paths from A, all the paths from A to B go through C, if a condition on C, then A and B are independent. Okay, so conditional independent, A and B are conditional independent of a third set C if all nodes in A and B are connected through nodes in C. It's the same idea. It's basically think of the graph. I chop off remove all the nodes related to C. If the two things are separate subgraphs, then it's conditionally independent. Okay, that's a very simple idea. And local Markov property just means that if I have a variable or a node X, okay, if I pick the neighbors of X, okay, given the neighbors of X, that node is conditionally independent of the rest of the graph. That's the same idea, right? I'm picking A as the one node, dropping all the neighbors of it, okay, which means that every path to remaining graph is gone. That means that node is conditionally independent of everything else given its neighbors. Okay, that's local Markov. So here was an example. So x1, x2, and x3 are conditionally independent of x6, 5, and 7 if I give you 4. Okay, because every path is severed from this side to that side. Okay, and local Markov property lets you infer things like x4 is conditionally independent of x1 and x7 if I give you these guys, neighbors. If I give you the neighbors, everything else is it's conditionally independent of everything else. Okay, I don't know. Yeah. So looking at the graph, what factorizations can you write? So here I wrote a couple of factorizations. So I saw the cliques, which are these, just this biggest clique over here, this clique, and this clique. So that's why there are 4 factors. I could have written additional factors with just smaller ones, 1 to 2, 1 to 3, 3 to 4, all the edges basically. That's it. But it turns out that the largest cliques are sufficient in a sense. Okay, so people only write the largest cliques. Okay, maximal cliques. So anyway, that's a side point. But the key point again is that given all factorizations of joint distribution, a graph will impose some conditional independence properties, and therefore there will be some restrictions on the factorizations that are allowed. If I tell you the graph, if I tell you the joint distribution, there is nothing you can infer. If I give you the graph, there are only certain factorizations that are allowed. Okay, that's the key idea. Okay, yeah, and as I was saying, why do we need to look at directed and undirected? the whole point is that there are some graphs, like for example, we cannot draw a directed graph if we have a joint distribution between 4 random variables where we want to impose that A and C is independent of B and D, A is independent of C given B and D, and B is independent of D given A and C. You can try to draw, I mean, what type of graph would agree with these two, and you will not get a directed graph. Okay, you can try this on offline. Same thing with there are certain independence properties, like for this 3-node graph, you cannot draw it in a undirected version. So that's why we looked at both undirected and directed ones. Okay. So that's kind of the summary. Is it? Yeah. So we have product as in factors for both directed and undirected graphs. Undirected graphs factors are called, I guess, potentials, and they're arbitrary. They're not conditional probabilities, whereas here these are conditional probabilities. Cycles are allowed. You just saw, you can have cycles, right? These guys were essentially cycles. There's a cycle over here. Sorry. So cycles are allowed. Cycles are not allowed. There's something called, so the Z is called a partition function. So some name from statistical physics, but physics mechanics. So Z, there will be some normalization because the factors are not conditional probabilities, whereas in this case there is no need to factorize. And independence check, local Markov property and global Markov property, and in this case d-separation. So it's a little bit more involved for the directed one. And inference, actually we'll see inference in a subsequent lecture. So we'll look at Monte Carlo methods, skip sampling and stuff. Okay. So that's the difference between those two. Any questions about directed and undirected graphs? No questions? Okay. So summarize, what do we do? Graphical models are good at capturing domain knowledge, basically capturing complexity and uncertainties. Things can be random. So you can assume that your linear regression coefficients are not fixed unknown, but could be random, for example. It captures conditional independences. That's what we spend most of the time today. And basically it's a tool for visualizing what's happening in a distribution. Okay, for small number of random variables, there's like the student network that we saw, SAT scores, intelligence, and it's kind of easy to, it helps you gain a lot of intuition about what's happening in your particular in that domain. Okay. Why graphical models themselves, mixture models, and Gaussian mixture models. Did you guys see Gaussian mixture models before? I teach it in 575. So mixture models are essentially also graphical models, very simple. Factor analysis, hidden Markov models, column filters, LDA, naive Bayes, everything, all of those are graphical models. Okay, and subsequent lectures we'll see inference and learning, but the next lecture we'll look at a mixture of graphs and deep learning. Okay, which how do you do graph processing tasks like solving like doing some prediction problem on structured data, which is not text or images, but a graph. It's a combinatorial structure essentially. Okay, that's it for today. So